Hello and welcome back to my Physics Online video lecture series. Today's video I wanted to look at the second part of my lecture set on oscillations and waves. This set of lectures covers all of oscillations and waves that I'm going to cover in my Physics 2 courses. Part 2 is going to cover the simple harmonic oscillations. Basically what we're going to do is we're going to look at two basic types of oscillators. We're going to look at springs and we're going to look at pendulum. These are the main types of things that are going to undergo simple harmonic oscillation. And of these, I would say the simplest is going to be the spring, particularly the ideal spring. And before we jump into the ideal spring and the ideal simple harmonic oscillator, I should note that not everything that undergoes periodic motion is going to be an oscillator. Not everything that is an oscillator is a simple harmonic oscillator. The simple harmonic oscillator is going to have two basic assumptions. The first is that you have a force which obeys Hooke's law. So that means that the force is linearly proportional to and in the opposite direction of the displacement. It has to be a linear restoring force, in other words. The other assumption is that we basically ignore all other forces that act upon the system. So we ignore other restoring forces. There's going to be no damping. There's going to be no friction. You don't have a driving force for the system. And basically, these are the two assumptions you're going to need in order to have a simple harmonic oscillator. So with that said, what's so special about Hooke's law? Well, let's consider our simple ideal spring. Ideal spring, again, means that the spring is massless, it's frictionless, there's no damping forces involved, we've got no driving forces involved. We're operating entirely in the linear elastic regime for the spring. So this spring is at equilibrium. There's a mass attached to one end. The other end is sort of fixed. And you can take that mass and displace it by some distance x. And when you displace it by some distance x, there's going to be a restoring force in the opposite direction from the displacement. So the shaded block in these two diagrams represents the equilibrium position. Here we've stretched the spring, here we've compressed the spring. Both cases you have a force that points towards the direction of equilibrium. And for our ideal spring, the vector force is related to the vector displacement from equilibrium by this equation. Force is equal to negative spring constant times x. So let's now consider that in terms of the other laws of motion that we know. Specifically, we'll look at Newton's second law. So Newton's second law, you'll recall, says that if you take all the forces that act upon an object, you add them all together, that sum of forces should be the object's mass times its acceleration. And so in this case, ultimately you get an acceleration which is proportional to the amount of displacement that you have in the opposite direction of the displacement, but ultimately the acceleration is linearly proportional to the displacement. So here is that equation. The acceleration is spring constant over mass times the displacement. That's basically substituting Hooke's law in for all the forces. That's the only force acting on the system, and then solving for the acceleration. So the first thing to note here is that because this right here is not a constant, once you release the block, it starts moving, therefore the displacement starts changing. That means that the acceleration is not constant, and so the constant motion kinematics equations that we did last semester no longer apply. We need to get a new equation of motion. So to get that equation for motion for the ideal simple harmonic oscillator, you can do this mathematically. We can also attempt to do it experimentally. Now, if you are doing a physics with calculus course, we're able to do it mathematically. Basically, your Newton's second law equation becomes this second order differential equation. So you have this derivative squared of x by dt squared is equal to ks over m x. These two added together equals 0, or in other words, this is equal to negative of this. The derivative squared of x is some constant times x. So this is mathematically called an ordinary differential equation. It's second order because you have a second derivative here. So how do you solve for this equation mathematically? Well, what you want is some function x of t which satisfies this equation. And in other words, if you differentiate x of t twice, you get some constant times x. And so one way of doing that is you basically guess the form of the equation. An exponential would work. Also, these cosine and sine terms will work. So I'm going to show actually one way that you can get that result for this particular equation. So first of all, in case you are lost as to where that equation came from, we started off by having basically sum of forces is mass times acceleration, Newton's second law. And we note that acceleration by definition is the second derivative of displacement with respect to time. Okay, so combine these two equations, you get basically sum of forces is equal to mass times d squared displacement by dt squared. Now, the only force that acts on the system is Hooke's law. So Hooke's law is the F equals negative k times x. So substitute this in, and what you end up getting is negative ks times x is equal to m d squared x by dt squared. Okay, so now in this form we actually can basically go to solve. Basically, to get the equation that I showed on the slide, you just add this term to both sides. You have 0 equals this plus this, then divide both sides by m. So I'm going to rearrange that basically to say d squared x by dt squared is equal to basically a negative ks over m times x. Alright, so how can we solve this equation? Well, if this was a ordinary linear differential equation, something of the form like dx by dt is equal to some constant times x, the solution is very easy, right? You can divide both sides by an x, you can multiply both sides by a dt, and you'd have something like dx over x is equal to c dt. So we can now integrate both of these. This one ends up being the natural logarithm of x. This side over here basically gives you something like a ct, and so therefore you'd have something like x equals e to the ct. Okay, and so on. Now, that's not actually what we have over here, though. What we have is a d squared x equals negative some constant times x. Alright, so one way of solving this is you can basically try to guess some solution. And this thing is basically saying, find for me the function such that d squared x dt is equal to some constant times x. Well, and negative. Well, let's say that x is equal to the cosine of the square root of that constant times t. Alright, so what would happen if we took some derivatives? Well, what is dx by dt? Well, take a derivative of a cosine, you end up with a negative sign. Got a negative sign, the square root of c is t, and you have a square root of c out front. Alright, well, in order to get d squared x dt squared, we need to take a second derivative. So d squared x by dt squared should be square root of c times square root of c. So that should be negative c. Derivative of sine is actually a cosine. So negative c cosine square root of c times t. Okay, so now question, does this actually satisfy this condition up here? The answer is yes, because this right here is in fact the expression for x. So this right here satisfies d squared x by dt squared is equal to negative cx. So that means that a cosine is going to satisfy this equation where c becomes the square root of ks over m. And you can try this also with a sine instead of a cosine if you want, and you'll see that it still satisfies this equation. You can do stuff like adding a constant phase inside of the cosine, and it still is going to satisfy the equation. And so what we've done here is we've solved this simple differential equation. You can see from this solution that this equation right here, x equals a cosine omega t plus phi, or this equation, x equals a sine omega t plus phi, are both going to work. Another equation that would work, although I'm not going to do it here, is x equals a e to the I times omega t, where omega is given as the square root of ks over m. All this stuff actually introduces a few new terms to our vocabulary, at least as regards oscillators. So oscillation, that one is almost a gimme from our periodic motion discussion in part 1 of this lecture. One oscillation is going to be a complete cycle of motion. Motion has to be cyclic, it's going to be periodic, it's going to be repeated. Okay, no problem there. Amplitude is the a, or the x max in that equation that we just wrote down for the solution of x of t. It's basically how much displacement can the oscillator have from equilibrium at its maximum displacement. It goes this far away and no farther. Very often, though not always, this is treated as the initial displacement. Why not always? Well, I can pull a mass away from equilibrium on a spring and then give it a push instead of releasing it. And if I do that, it's going to mean that the amplitude is not my initial displacement. It'll be somewhat larger than my initial displacement. The other thing that does is it adds the need for a term like this phi for phase. Usually, if you just pull out to some initial displacement and then start the timer when you release it, then you can describe this motion as just x equals a cosine omega t, and you can ignore this plus phi. And in that case, if you wanted to write it as sine, you'd have plus pi over 2. This phase is always in radians. So the phase basically is telling you, are you actually at the amplitude at time 0 when you release it, or at time 1 period, or what half a period. Okay, the period, big T, is how much time does it take to complete a single oscillation. So when I say at 1 period, that means you've completed 1 full oscillation. Half a period means you've completed half the time of that oscillation. Frequency is actually the inverse of the period. It's the number of oscillations per unit time. So whereas period has units of seconds, frequency has units of inverse seconds or hertz. And then this omega term, lowercase omega, is angular frequency, has a very similar definition to its definition in rotational motion when it represented the number of radians per unit time. So a complete circle is 2 pi radians. A complete oscillation is equivalent to a complete circle. So this angular frequency is equal to 2 pi times this frequency. It's also equal to 2 pi divided by this period. So let's look at what a simple harmonic oscillator would look like graphically. Make these graphs by, for example, attaching a marker to your mass that's on the end of a spring, pulling the spring and releasing it, and then maybe cranking a piece of paper through the marker, as to make this one, as the thing oscillates, linearly cranking it. This one, you can't get quite like that. You'd have to maybe use a photo gate to measure the speed or to measure the acceleration. Turns out, though, that this is basically what these graphs will look like. We're assuming that you have some equation like x equals a cosine omega t, and to do that, you basically would be pulling the mass out to the amplitude and then just releasing it and letting it go. All right. So the other thing to notice about these, for one thing, they all look like sine or cosine waves. Second, you'll notice that they look like they've been shifted by some phase. So this one starts off at the amplitude A. When we're half a period done, it's at negative A. When we're a quarter of a period, it's at 0, that's equilibrium. 3/4, you're at 0, that's equilibrium. 1 period, you're back to where you started, full displacement. If you look at the velocity versus time, you'll notice that you start at 0, so initially it's at rest. Then you're at 1/4 of a period, you're at the maximum displacement away in the compressed direction. Then you get back to 0, then you're at the maximum in the stretched direction to 0. This looks like we've taken this sine wave and shifted it by pi over 2 in this direction. In other words, we've shifted it by 1/4 of a cycle, 1/4 of a period in this way. And this acceleration looks like we shift by another quarter period from this velocity cycle. So each successive one of these kinematics graphs is shifted by 1/4 of a period from the last one. What I'd like to do at this point is obtain an expression for the period of the spring oscillator as a function of some of the actual properties of the spring, or maybe of the spring earth system. And so what you see here, this is actually a screen capture from one of those simulations that the Colorado physics education team has put together. You can go run this simulation on your own. I'm not going to do that in this particular video. But basically, I want to, either by experiment in the lab or by simulation with the Colorado PHET program, obtain the relationship between period, which is how much time it takes to complete an oscillation for the spring, and some of the basic parameters like mass or spring constant, the initial displacement, which is the same as the amplitude, and the gravitational acceleration. Basically, the way that I'm going to go about this is I make a set of plots like what you see here. So these are mostly experimentally generated. Of course, I had to do the simulation for gravitational acceleration versus period, but the rest I can do experimentally in a lab. Basically, you vary one parameter at a time while holding all the other parameters constant, and you see how long is the period of oscillation versus whatever parameter that you're varying. So in this case, I'm varying the amplitude, which is the initial displacement from equilibrium. In this case, I simulate a variation in the gravitational acceleration. Here I'm simulating the changes of mass and how that affects the period of the spring. In this one, I'm changing the spring itself, so I have a different spring constant. I'm seeing how that affects the period of the spring. And looking at each of these graphs, we notice that some of these plots are actually constant. So the period is not dependent on amplitude, for example, because you could draw a horizontal line of best fit for this plot. It's not going to depend upon the gravitational acceleration. You can draw a horizontal line of best fit for this plot. You might want to ask yourself at this point if either of these are what you would expect. Okay, now let's look at the period versus mass and the period versus spring constant. These two are obviously not constant periods. There's some real variation here. This one implies that the period does depend on the mass and on the spring constant. So what we do is we take each of these graphs and we try to get a line of best fit for them. So one way of doing that is that this one had looked like it might be a parabola, for example. So we try squaring the axes. In this case, I squared only the neither axis really, and this one I squared the period axis. So here you have a sideways parabola, here you have a straight line. And anytime you have a straight line, you can write y equals mx plus b. So the thing on the y-axis is period squared. B is the y-intercept, it goes from 0, 0. X is whatever is on the x-axis. So our equation is of the form period squared is slope times mass. So we've got to find the slope of this line, and then we have an equation relating period to mass. And in this case, the slope was actually given by 0.46 seconds squared per kilogram. So that might not be a unit that we've seen much of, but it actually turns out to be a familiar unit. So this is the equation with numbers in. And we can go through the same process with a varying spring constant. Alternatively, we could have made several of these plots, one each for 2 or 3 different spring constants, or 5, or however many springs you have available. You'd expect to see a line for each spring. The question is, does the line change? Does the slope of the line change when you change springs? And the answer actually would be yes, and you know that it does because you see from the original period versus spring constant that you get not a constant period. So we go through a similar analysis with period versus spring constant. Basically, we invert the axis. In this case, we look at frequency versus spring constant. We get something that looks very much like our original plot of period versus mass. Sideways parabola, in other words. So we go through the same process of squaring an axis, getting a line of best fit, doing a y equals mx plus b thing, seeing that in the y-axis you have a frequency squared, on the x-axis it's a spring constant. And so you end up with some equation that looks like this. And again, you get some very strange looking units. It turns out that these units will actually simplify. So seconds squared per Newton per meter simplifies to some other unit that you've seen a little more often. More on that here. We notice that the units are equivalent for the first set of graphs, the period versus mass graph, to meters per Newton. For that second graph, the simplification is that seconds, inverse seconds squared divided by newtons per meter is the same thing as kilograms. So one possible explanation for that is that the slope of the period squared versus mass is 1 over the spring constant, and the slope of the frequency squared versus the spring constant is 1 over the mass. And it turns out that if you look back at the numerical answers we calculated for these two slopes, 0.46 seconds squared per kilogram is off from the spring constant. You know, the spring constant was 85 newtons per meter. If you divide 1 by 85, you don't get 0.46. In fact, you're a factor of about 40 too large. And then similarly, if you divide 1 by 1.05 kilograms, you don't get 0.024 inverse kilograms. You actually are again off by about a factor of 40. Okay, so that factor of 40 actually comes from a 4 pi squared. If you multiply 4 times pi squared, you get about 39.5 or 39.6. It's very nearly 40. Okay, so putting all of that together, you can see that period squared looks like slope times m. You can see that 1 over period squared is slope times ks. If you combine these two statements and you combine that factor of 4 pi squared, what you end up getting is that the period squared is 1 over the frequency squared, which is equal to 4 pi squared m over the spring constant, mass over spring constant. So if you take a square root of everything here, you get that the period is 2 pi square root mass over spring constant. So let's look at a few very simple examples, just to put a few numbers to all of this theory that we've done. So let's say that I have a spring and the period of oscillation is 4 hertz. Excuse me, the frequency of oscillation is 4 hertz. What is the period? So this is a simple gut check. Do we know how frequency and period are related to each other at this point? And since period is equal to 1 over the frequency, we should be able to divide 1 by 4 and get what the period is. So the period should be 1/4 of a second. Every 1/4 of a second it completes 1 oscillation. That means that it'll make 4 whole oscillations in a second. Okay. Now let's say that you've got an ideal spring, and the spring constant is 100 newtons per meter, and there's a mass of 100 grams on the end. So what's the period of oscillation going to be for this spring? Okay, so here's a slightly, maybe we have to use a calculator or something. Now the period, again, T is equal to 2 pi square root mass over spring constant. We just gave that the mass was 100 grams. So that is the same as 0.1, maybe 0.100 kilograms. The spring constant was 100, just 100 Newton per meter. So that means that this period must be 2 times pi times the square root of 0.100 kilogram divided by 100 newtons per meter. So whip out your calculators, and just a little shy of 0.2 seconds. So this is actually 0.19869 seconds. So if we're going to round off to 3 significant figures, you end up with 0.199 seconds. So that's the period of your spring. All right, last but not least, let's say you've got an ideal spring with a frequency of 0.25 hertz and a mass of 1 kilogram. So can we get the spring constant out of that? It's just a reworking of the previous equation. So again, we have that the period, which is 1 over f, is 2 pi square root m over ks. Thing that we are looking for in this question is the spring constant ks. So we're actually looking for this term right here. So solve. So t squared is 4 pi squared m over ks. Therefore, ks must be 4 pi squared m over over t squared. And m over t squared is the same thing as 4 pi squared mf squared, mf squared. Okay, so spring constant in this case should be 4 times pi squared times our mass was 1.0 kilograms times the 0.25 inverse seconds squared. So that gives us about 2.45, about 2.47 seconds. We only had two significant figures, so we need 2.5 seconds. Alright, so now we have obtained, basically experimentally, the rest of our equation of motion for a spring. Again, if you wanted to get the actual form of the equation, you could do some setup like this where you get a mass on the end of a spring with a little marker or a blotter or something, and then a paper that you sort of roll linearly with time. And it will, in fact, make this sinusoidal curve. Of course, it's a little messed up right here. It should actually be continuing upward. But you'd get basically a sinusoidal curve. You can fit to it the equation that it's the amplitude, which is this maximum displacement, times the cosine of omega t, which is the same thing as the cosine of 2 pi times the time divided by the period. And ultimately, in terms of properties of the spring, you'd have whatever the maximum displacement is times the cosine of the square root of spring constant divided by mass, square rooted times the time. So that basically is how you get the equation for the displacement versus time of this simple harmonic oscillator spring. And all the other simple harmonic oscillators will follow an equation that is like this equation. So this basically is our boxable equation. It describes a simple harmonic oscillator in general. This one does. This describes specifically the ideal spring. There is an alternative derivation which is possible for those of you who are using physics with calculus. Again, you have a second order differential equation, which I sort of solved for you earlier, but the solution to this equation basically occurs when this omega squared is equal to ks over m. So this right here, this equation equals 0 when omega squared is ks over m. And so that means omega has to be square root of ks over m in order for this to be solved. The rest of this I derived earlier, so I'm not going to rehash that whole derivation. It's basically just solve the differential equation that you have here. And so here is the summary of the equations then for our simple harmonic oscillator. These two I didn't derive. I just am stating that these are the equations. For those of you who are in the physics of calculus class, it's actually straightforward to get these two equations. You just take a first derivative of this equation to get velocity, you take a second derivative to get acceleration. And experimentally, these can be obtained by just basically doing like a photo gate to measure the speed everywhere, or a motion sensor to measure the speed everywhere of the oscillator, and ditto for the acceleration, and they will in fact follow these two equations. You can also see it from those graphs that I put up quite a few slides back. So let's do a slightly longer spring oscillator example. Okay, so you have an ideal spring. It's being stretched by an amplitude of 0.25 meters. It's released as a period of 2 seconds. It's got an oscillating mass of 1 kilogram. So to write all of that out, we have amplitude is 0.25 meters. Period equals 2.00 seconds. And mass is equal to 1.00 kilogram. Okay, so the first question is, what is the simple harmonic oscillator's spring constant? So it's the spring constant of this spring, in other words. Well, recall that the period is given by 2 pi square root m over ks. So if we want to get the spring constant, we rearrange this equation to get that ks is equal to square both sides, divide both sides by t squared, multiply by ks. So you have 4 pi squared m over t squared. So it's basically going to give you 4 times pi squared times 1.00 kilograms divided by 2 squared is again 4 seconds. So pi squared is what falls out of this. You basically end up with a spring constant of actually very close to 10. It turns out that pi squared is approximately equal to 10. It's at 9.869. So we'll call that 9.87 newtons per meter. So if we wanted to do a very quick approximation, we'd call it 10. Okay, part B. What is the maximum magnitude of the velocity? So, in other words, what is the maximum speed that this oscillator is going to have? So, to do that, we can use this speed equation that we obtained. Basically, it looks like A square root ks over m times the sine square root ks over m times t plus phi. Now, you may be looking at that and saying, okay, how am I going to get a maximum speed out of this? And the answer is that this whole part of the expression has a maximum value of 1. So this whole expression is always greater than or equal to -1. It's always less than or equal to +1. Basically goes from +1 to -1 and back. So the maximum value of the speed is when this has a value of either plus or minus 1. And so basically V max, therefore, is going to be given by the amplitude times the square root of ks over m. So that's 0.25 meters times the square root of that 9.87 newton per meter that we just got in part A over 1.00 kilogram. Yep. So the maximum speed that this guy has, you would expect to about a little over 3/4 of a meter per second, 0.785 meters per second. Okay, part C. What's the maximum magnitude of the acceleration? That one is even more straightforward. You can actually just use Newton's laws to do that and figure out that the maximum acceleration is when you have a maximum force, which is when you have the maximum displacement. The other way you could do it is you could use the equation that I just showed for the acceleration. Either way, so with that one you end up with a cosine term which still has these same rules, and so you end up with A max is equal to all the stuff that's outside that cosine term. So that's amplitude times ks over m. So we basically do the same calculation again, but without taking a square root. So that's basically 0.25 meters times 9.87 newtons per meter, and then we're dividing that by basically by a kilogram, and so that gives us 2.47 roughly, 2.47 meters per second squared. This right here is a mass, so it's kilograms, this is newtons per meter, this is meters. So if you check all those units, you get meters per second squared, which is what we want. Okay, so then last but not least, there is the question of where is the spring and what is it doing at time t equals 1.5. Okay, well, there's basically two ways that we can go about doing this. One is the physically intuitive way, and the other is the grind it out with math way. The grind it out with math way works just fine. What you basically do is you take these different equations. So we have a position versus time equation, we have a speed versus time, we have an acceleration versus time. Or a velocity and an acceleration versus time, if you will. And we basically plug in this time equals 1.50 seconds. So you'd have, for example, x is equal to the amplitude times the cosine of really, you can write it as 2 pi over t times t, since we have this t. So basically a cosine omega t. And we just plug in our numbers. So this is 0.25 meters times the cosine of 2 pi divided by 2.00 seconds times 1.50 seconds. So notice 1.5 divided by 2 is 3/4. We're multiplying again by 2, so this is basically going to be you can call it 1.5 pi, or 3 pi over 2, in other words. And cosine of 3 pi over 2 gives us a value of 0. So actually at this time it's at the equilibrium position. And we can repeat this for the velocity, and we can repeat it for the acceleration. But having solved this part of it, having figured out that it's at equilibrium, so x equals 0.0 meters, that's equilibrium. Alright, we can plug in again for v and for t, do it the math way. Here's where the physics intuition comes in though. If it's at x equals 0, it's at equilibrium, that means that the net force at that time is 0. So there's no net force acting on this object. If there's no net force acting on this object, what's the acceleration got to be? Well, a must be 0. And furthermore, when a is 0, that's when speed is at its maximum. So we already figured out what the maximum speed is. So v must be equal to v max is equal to 0.875 meters per second. Alright, so those are the answers to this spring oscillator example. next thing that I wanted to talk about, next kind of oscillator, is the pendulum. And in the simplest case, the pendulum is going to consist of a long string, which is massless or nearly massless. It's an ideal pendulum that's massless, but it's a good enough approximation that the mass of the string just be less than the mass of the bob, which is suspended at the end. So the top of the string is fixed in place, the rest can swing freely. The bob has a mass that is much larger than the string's mass. Other than that, the mass of the bob shouldn't matter. And the diameter of the bob should be much less than the length of the string. In fact, ideally, it is a point mass. And as long as you choose a small angle as your maximum displacement, your amplitude of displacement in other words, this will move like a simple harmonic oscillator. And again, this imposition that says we need to have a small maximum displacement, operationally, if you're in the lab, you maybe are using a protractor, it's marked off in degrees, so maximum displacement of 10 degrees or less, no problem. It should act like a simple harmonic oscillator. In actuality, you're going to want to measure, or in your theory, you're going to want to have this angular displacement in radians, and the rule is basically that you want this maximum displacement to be much less than 1 radian. The other thing about this is that this maximum displacement being relatively small is true for springs as well. I already mentioned that a spring is only going to work as a simple harmonic oscillator as long as it's in the Hooke's law regime. That is, in fact, the linear or elastic regime of the spring as an elastic object, the spring under tensile stress and strain. And so that happens for up to a certain maximum amount that you can stretch the spring before it enters the plastic regime. So the pendulum is actually not that different from a spring in this sense. So let's look at the restoring force on the pendulum, because in the spring the restoring force was from Hooke's law. So what is it for a pendulum? Well, here you can see a simple free body diagram. And basically you have your mass at the end of the string. The string makes some angle theta with the vertical. And that also means that if you continued this string, it would make an angle theta with respect to the force of gravity, the weight. So here's the weight. T represents the tension in the string. These are basically the two forces that are acting upon this pendulum. And so the net force is going to be the vector sum of these two, might be something like this. And as long as you have a very small angular displacement, this net force actually is going to more or less be horizontal. The motion is more or less going to be a horizontal motion. And so the main restoring force you can write as being the x component of gravity, because the y component of gravity here is actually going to cancel with the tension, or is going to provide, if not a cancellation, is actually going to provide the centripetal force, because if you were to complete a revolution with this, you'd have circular motion. So you actually need to have a balance between tension and the y component of gravity for your centripetal force. So the x component is the one that's important here as our restoring force. And basically, if you have a sufficiently small angle, the sine of theta can be approximated as theta. The reason for that is that we can actually express the sine of any angle, any arbitrary theta or x or what have you, as being a sum of powers of x. This is what's called a Taylor expansion. And it turns out that the sum of powers of x, the first term in this expansion is just x, or theta as it is. The second term is a minus theta cubed over 3 factorial, and then a plus theta to the fifth over 5 factorial, and so on. Well, if theta is much less than 1, then theta squared is going to be much, much less than theta. Theta cubed is going to be much, much, much less than theta squared, and so on. So all the terms except for that first one disappear from your polynomial. And so this restoring force ends up looking like FGX equals mg theta, or thetas in radians. And it's actually then a very similar force to the Hooke's law. You could think of it one of two ways. One is that the displacement is this angle away from the vertical, and in that case the force as a function of this angle is about equal to mg times the angle. So that's exactly like Hooke's law. We replace the spring's constant with a mg. The other way to look at it, of course, is that the displacement is entirely a horizontal displacement, and that works, again, as long as this angle is very small. For a small angle, you don't have much change in the vertical distance, but you might have a substantial change in the horizontal displacement. And in that case, you basically would have that your displacement x is equal to whatever this length is times the sine of theta. And so that total displacement, again, ends up being a function of this angle theta. Basically, you end up with x is approximately equal to L theta. So again, or conversely, the force is equal to mg x, basically x over L. And so you can go through similar analysis with this to what we did with the spring, and you'll obtain fairly similar results. You're going to get a different expression for angular frequency and so on. Turns out angular frequency is a function of the free fall acceleration and the length of the string. So the mass doesn't matter, the displacement doesn't matter, but only free fall acceleration and length. Basically, we have these parameters that I got in the first part for the ideal spring. You have an analogous parameter in each case for the pendulum. So for example, your displacement, you could use x for the spring, or delta x. Here we might use a delta theta, or sometimes just simplified to theta. You can in fact also use an x. Your restoring force, you're going to be describing, in the case of a spring, Hooke's law, it's negative ksx. In the case of a pendulum, it's mg theta. So mg times displacement, k times displacement. Period, 2 pi square root 2 properties of the spring, 2 pi square root a property of the pendulum, a property of the earth, so basically 2 properties of the earth pendulum system. And then the position looks like a maximum position times the cosine of 2 pi times t over a period, and ditto for this one. Or if you want it in terms of x, it's going to look like this. So you can do a side-by-side comparison of both the pendulum and the mass. And so basically you have some maximum displacement, gives you a maximum acceleration, velocity is 0 at that point. You release it, Pendulum swings through its equilibrium, the spring moves to equilibrium. When it's at equilibrium, there's zero acceleration in both cases, you're at a maximum speed in both cases. Swings through to the opposite side, you basically end up in the ideal case with the same displacement from equilibrium as you had initially, just in the other direction. So theta max, delta x max, maximum acceleration, zero speed, and so on. Motion just keeps repeating back and forth between the two amplitudes. So this also means that the motion of the pendulum can be described using sine and cosine waves, just like a spring. Let's do a few short examples just to put some numbers to all of this. Suppose that you're going to build a clock. You're going to use a pendulum. You want 1 second per oscillation while on the Earth near sea level. So the question is, how long do you need to make the pendulum be, and how much mass would you want to attach to the end of it? All right, so again, the period in this case is 2 times pi times the square root of L over G. So we want the period to be 1 second per oscillation. So T is 1.00 seconds, G 9.8 meters per second squared. We're solving for how long this guy should be. So length should be T squared G over 4 pi squared. So put all that in. You end up with just shy of a quarter of a second. So this is 0.248 seconds. Quick rule of thumb here, by the way. If you want to build a ideal pendulum on the Earth with a length of 1.0 meter, sorry, this is 0.248 meters. If you have a 1.0 meter long pendulum, you're going to have a period of very nearly 2 seconds. It's actually 2.01 seconds if you round to 3 significant figures. So your rule of thumb basically is a 1 second pendulum is about a quarter of a meter long. A 1 meter long pendulum gives you a 2 second period for oscillation. So follow-up question, suppose you took this pendulum to the moon, what is going to change? On the moon, gravity is about a 6th as strong as on the Earth. Mass doesn't matter here, it doesn't matter here. So I guess the question remains, you want to keep time in seconds, 1 second per oscillation. How long do you need to make the pendulum now? Well, L is still going to be T squared times G over 4 pi squared, where G becomes G prime, or G moon. So L basically is 1.0 second squared times 9.8 meters per second squared divided by 6 if we're on the moon, over 4 pi squared. So how long does the pendulum now need to be? Well, it needs to be a 1/6 as long as before, or in other words, 0.0414 meters. So reduce gravity by a factor of 6. You want to keep the same time. That means you got to reduce the length by a factor of 6. Okay, so what happens if you don't have that nice ideal pendulum that we've been using so far? Maybe you have a real, or sometimes it's called a physical pendulum. Physical pendulum basically means instead of having a massless string and a diameterless bob, you have an actual extended body. Maybe you hang a guitar case or a caveman's club or something. So we'll suspend the object at point O. is the point at which the object oscillates through. So this could be, for example, a pin stuck right here. It could be a pin stuck at the end, etc. Usually it's not at the very end. And the one rule is that it can't be at the center of mass of the object. And in order to analyze the physical pendulum, we actually end up needing to use our rotational motion equations. Torque equals moment of inertia times alpha, rather than force equals mass times acceleration. So recall that the torque is given by the cross product of R cross F. So torque is going to be basically the force times the distance at which that force is acting from the suspension point times the angle between them, the sine of the angle between them, and then of course in the perpendicular direction to the lever arm and to the force. And so in this particular case, we might use LCM, so the force is the weight of this object that's acting at the center of mass. That's the distance from the center of mass to the suspension point times the actual weight of the object times the sine of this angle between the line straight from suspension point to center of mass and the vertical line. So theta, in other words, is this angle right here. So to get the equation of motion, we use the angular acceleration alpha rather than the linear acceleration a. And actually from here it becomes very similar to the analysis that we've done for a spring or for a pendulum, because alpha is d squared theta by dt squared. And Newton's second law in rotational motion says that the torque is equal to the moment of inertia times the angular acceleration. So I times d squared theta by dt squared, that's the I alpha side, here's the torque side, is equal to negative mg LCM sine of theta, maybe a theta hat if you want to specify a direction. Or you can specify it as the z direction, as the case may be. And so in this case, you really need that Taylor expansion that I described earlier. So here is the Taylor expansion explicitly. Sine of theta is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, etc. So here's the whole expansion. And again, if theta is much less than 1, then this term is vanishingly small compared to this term, and this term is vanishingly small compared to this term, and so on. So all these other terms vanish, and you're left with sine theta is about theta. So now your equation of motion looks like this. I've basically divided everything by the moment of inertia. I've replaced sine of theta with theta. So left with d squared theta over dt squared equals mg L center of mass over the moment of inertia times theta. Look, it's the same equation. If you changed out the theta for an x, if you changed out this term right here for a k over m, it's the exact same equation we had for a spring. So that means that it's got to have the exact same form of a solution. So this is the solution for the moment, for the motion. So here is the angular displacement as a function of time, where we have a slightly more complex equation for omega. It's mg times this length times whatever the moment of inertia of the whole thing is. But, I mean, this is a bunch of constants that are properties of the pendulum itself. So it's not a totally unreasonable equation that we end up with. It basically looks very similar to the same simple harmonic oscillator equation that we've been using for both the spring and for simple pendulum. We just change the meaning of omega, change what omega is equal to. It still means the angular frequency. Alright, so let's close out with an example of an actual physical pendulum. So we take a meter stick and we basically suspend it from one end. So the suspension point to point is the very end of the meter stick. Has a mass, big M, has a length, big L. Probably big L is 1 meter since it's a meter stick. And you'll recall from your Physics 1 class that the moment of inertia for a meter stick is going to be the same as the moment of inertia of a long cylinder, basically. And we're going to treat it actually as a long, thin rod. So part A of this example is to remind you that you should probably go look up or else otherwise calculate the moment of inertia using the table in your book. Of course, if you want to calculate it by hand, you'll recall that the moment of inertia is, for a bunch of discrete objects, sum of the individual masses times the individual distance of each mass from the axis of rotation squared. And so if you have an extended object of some sort, you can usually end up doing this by taking an integral. This usually becomes something like integral of r squared dm. And in this case, dm is some basically function of the linear length, and r is also some function of the length. So this might be something like lambda dx, and r is equal to some x basically, where the total mass m is lambda times the total length, or in other words, lambda is defined as the mass per unit length of this meter stick. So your moment of inertia, in other words, is going to look like the integral of x squared lambda dx, and that's from basically 0 to whatever is the length of this entire meter stick, because we're suspending it from the very end of the meter stick. And so this integral is going to be lambda over 3x cubed. We're going to evaluate from 0 to L. So that is lambda L cubed over 3. And of course, lambda times L is the mass. So this is mL squared over 3. And again, you could also just go look that up in the table in most books. So now we've got the moment of inertia in terms of the mass and the length. So part 2 was determine what is the period of oscillation, given that the mass is 0.1 kilogram and the length is, well, it's a meter stick, so length is hopefully pretty close to a meter. So what is the period going to be? Well, we had that omega is equal to the square root of mg L to the center of mass divided by I, which then becomes square root of m times g times L center of mass divided by m times total length squared over 3. Now this LCM, center of mass for a meter stick, is going to be the center of the meter stick. So this is actually a half of L. So we basically end up with omega equals square root of, let's cancel some combined units here, shuffle everything around. 3, so these two masses go away. It's actually 3g divided by 2L. Okay, and recall, of course, that the period is going to be 2 pi over omega, or omega is 2 pi over period. So that's going to be 2 pi times the square root of 2L over 3g. So what I'm getting for that is about 1.64 seconds. T equals 1.64 seconds. Quick double check is, remember the rule of thumb that I mentioned earlier. If you have a 1 meter long simple pendulum, the period will be 2 seconds. So what's a quick double check that we can do? Well, this physical pendulum is a total length of a meter long. So it should actually have a period which is shorter than the equivalent length of simple pendulum, and that is satisfied. And specifically, it should be a factor of the square root of 3 over 2 shorter, as we see from this equation over here. So is 2 divided by 1.64 the square root of 3 over 2? And the answer is, yeah, approximately. Okay, last part of this example I just did in doing this comparison, because the question was, how does it compare with something that has a length of 1 meter and is a simple pendulum? So T for a simple pendulum would have been 2.01 seconds. So T over TS should be approximately square root of 3. Should be approximately square root of 2 over 3 in this form. Alright, so that actually completes this video lecture. So this is basically lecture set 1, part 2 for the Physics 2 courses. And at this point, I hope that you have watched through all of this to get to the credits, if you will. But I hope that you found this video helpful, and thanks for watching.